Good morning, everyone. I hope you're all wide awake to start this day with a keynote about explainable AI. We're hosting this keynote as part of the European AI Week, an initiative by AI for Belgium to highlight the recent advancements in Belgium in terms of AI. And for those of you who don't know ML6 yet, ML6 is a services company specialized in artificial intelligence, and we help our clients adopt the technology and create value with it by building custom AI solutions and advising them on how to build their own capabilities. Our keynote today will be about how we look at explainable AI at ML6 and how we apply that in our projects. And our speaker is Arne Vandendorpe. Arne is a machine learning engineer at ML6. He works closely together with our clients to build state-of-the-art solutions uniquely tailored to their needs, and that mainly in the manufacturing industry. Before I pass the word to Arne, I would just like to mention that there will be some time for Q&A at the end of the session. So if you have any questions, you can drop them in the chat. And with that, Arne, the floor is yours.
All right, great. Thanks, Julie. So indeed, my name is Arne and I am an ML engineer at ML6. And today we're going to talk about explainable AI. So if we can just pull up the slides here, we can jump right in. All right, great. So maybe before we go into the content, let's take a minute to dissect the title. So as Julie said, it's about explainable AI. But then the second part, from Shapley towards AI design principles and human-centered machine learning. So let me address and give some notes on that, because we at ML6 have a rather unique definition and approach towards explainable AI. So whereas in the traditional definition, we often mostly look at the machine learning models and see explainable AI as an effort to make those black boxes, those ML models, more explainable, we see explainable AI as more of an effort throughout the entire project. So starting from the data, going through the model, and ending up with the user interface in the end, the user experience. So that's why we're going to go from Shapley values, which are a popular tool for the traditional definition of explainable AI. You might be familiar with it already, you might not, but don't worry, we'll address it. So we'll go from those, but also focus on the design principles. So how will this talk be structured? We'll start with the what and why of explainable AI in some more detail. And then we're going to look at those design principles. So really go into how at ML6 we tackle explainable AI. And then in the end, we'll apply what we've learned, and we'll take a look at one of our use cases where explainable AI has really been instrumental in building that confidence in our solution and building that human-centered solution that was ultimately able to drive the value. So without further ado, we'll jump right in. And I'll start by putting forward two statements. And the first one's in the title. I'm going to say there's a gap between the value that AI can generate today and its adoption by organizations. So that's the first statement. And then the second would be AI is in a very good place. And I'll first give some arguments to give some founding for the second one. So the first one is the massive research interest that makes AI to be in such a good place. And it's both from academia and big tech companies. And more of that, and that's my second point, more often than not, that research is then open sourced. And so they can build from each other, which means that there are constant improvements to the current state of the art. But on the other side, next to the research part of ML, it's also ready to generate value. There's proven return on investment across many different sectors. And also, these are becoming mature solutions. So the mature operations towards sustainability, maintainability, modifiability that we've come to expect from traditional software development, they are also being integrated into machine learning practices under the name of MLOps. And that's also instrumental in really making sure that these are mature solutions that we're creating. And then thirdly, they are future-proof by design because they have this self-learning nature, right? They can adapt to changing data, they can adapt to changing circumstances, and that makes them such a good investment as well. But so then returning to my first statement, so this gap between value and adoption. And this is really caused by the black box nature that is often a part of those AI solutions. Because we have often a solution or a model where we give some inputs and get an output and are not really sure what is happening in between, it makes it hard to reason about these solutions. It makes it hard to trust these solutions. So if we want to drive adoption here, we have to tackle this black box nature, and explainable AI is the way to do it. So then let's take a look at what explainable AI is exactly in our context. And we're going to do it by starting off with an example. So I assume everyone is sick and tired of hearing about COVID nowadays, but I'm going to do it anyway. And we're going to take a look at a hypothetical example. So I guess everyone is familiar with the Belgian COVID barometer, which monitors the current state of COVID and the current severity, and then gives a classification of we're in a green state, orange or red, and then really the restrictions that are put on events and such are then dependent on that, right? So assume we want to predict that using an AI model. Maybe you are planning your holidays a month in advance and you want to know what will the severity by then of COVID be. So you turn to your friendly neighborhood ML experts and you ask them to build you such a model. And after a week, 2 weeks, they return to you with this model and they're very proud to show you, look, we've made this AI model. It takes the current number of hospitalizations, maybe the degree to which the population has been vaccinated, an index representing the threat of new variants, current number of new cases, and so on. Takes all of that info and then gives you the prediction a week from now, a month from now, of what the state will be then. It gives you green, orange, or red. You think, great, I can start using this, and you do. So every day you follow it up, and hopefully you get, okay, it'll be green, it'll be green, it'll be green. But then at some point it switches and it says, no, a month from now, it'll be orange. Now this really messes up your holiday plans, for example. Way better would have been if we would have seen a distribution of these classifications, right? A month from now, there's a 55% chance of it being green, a 44% chance of it being orange, 1% red. Because that way we can see the shifting distributions as the days go by, and we have a lot more information to reason on. We wouldn't be so surprised if suddenly it tips to orange then. But now maybe with this additional information, so you have the distributions, you're faced with a different problem because you're seeing 44% orange. That's weird. Looking around me, there's barely an uptick in the current cases. A lot of the people are vaccinated. So where is this coming from? And then in the next iteration, what would be even better is if we can correlate that 44% back to its inputs, right? So this could be an example of an explanation to this 44% observation, where we see that the index representing that threat of new variants is really carrying the bulk of this output number. And so that makes it a lot easier to trust the explanations and the predictions made by this model, and not just discard them out of hand because they really go against your intuition. So because we see indeed the number of new cases barely has any impact on this figure, the number of vaccinations has a positive impact, of course, on this number, but then this threat is really carrying the bulk of it. And so what I'd like to stress here is that through these iterations that have made our solution more explainable, we have not fiddled with the model in terms of accuracy. We didn't need more data. The model didn't improve or get necessarily better in predicting it. It just has become more human-centered, more fit towards its context, and so more usable. So with this example being passed now, we can dare to put forward a definition of explainable AI. And again, I want to reiterate here, this is really ML6's interpretation of explainable AI, which takes a more holistic approach to the entire project in terms of explainable AI. So what is the definition then? Well, we see explainable AI as an ML engineering culture and a set of best practices that aims to then better leverage that human AI complementarity through explainability. So again, from data set through the model, ending up all the way into the human user experience. So now that we've seen an example, we know how we approach explainable AI, what it could be. But where exactly does it drive value, and what's its purpose in different scenarios? Well, it turns out there's three big scenarios, and they're all based on the performance of the ML model compared to its human counterparts. And let's take a look at the first. So where an AI model, an AI solution is weaker than its human counterparts. And there, adding explainability is really aimed at finding where our model struggles, finding those failure modes, finding those areas in our data where the model hasn't had enough data to learn anything significant, or that is too difficult for the model and the modeling that we're using. So one of the things that Explainable AI could do here is then promote active learning, where we take these very hard examples that the model struggles on and prioritize them in further modeling and further training. So through that active learning, we might then progress to the stage and scenario where the AI is on par with its human counterparts. And here, explainability is really about adding trust to the user, making sure that the user can reason about the model so that even when these predictions go against his or her intuition, you can still trust it, as we also saw in the example, right? And then we have the third scenario, and this is a bit of a separate one where the AI is stronger than a human. And this will often be the case when we have vast amounts of data. Imagine an aircraft, a Boeing 747, for example, that can every hour produce terabytes and terabytes of data. And so this vast amount of data is simply too huge for any human mind to really comprehend, to search for insights in, to search for correlations. And so there we could have our AI model or statistical model doing that for us. And then adding explainability on top of that is really to explain what the model has learned back to us, inform us humans about what it has learned from the data. So three separate cases where we actually drive the value. So now that we know the what and why and also the purpose in the distinct scenarios, let's go to the design patterns that I have promised when we were on the title slide. So we have 5 generic design patterns that we are looking for when tackling a project at ML6. The first one is problem reframing. Then we go on to interpretable models, feature attribution, transparency and transferability, and finally intuitive visualizations. So the first one, problem reframing. The question here is really about how can I reframe this problem in a way that the solution is inherently more interpretable and also valuable. And this is often very low-hanging fruit. So at the beginning of the project, take your time to identify how we can reframe it so that our life becomes easier down the line, so that our customer can get more out of it, and so that explainability comes out of the box. And the first example is the one on the left, where we had a customer in the car industry. And what they wanted us to do is, based on an image of a car or based on multiple images of a car, classify the state that the car is in. Has it been scratched? Has it not been scratched? Are there bumps in the chassis, for example? So really build a classifier for that. We took a look at this and then made a counter proposal where we said, okay, but instead of doing classification, if we were to do object detection and so localize where these scratches are, localize where these bumps are, that gives us 2 things. One, if we visualize this and show it to a user, they can very quickly confirm or dismiss one of these detections. And so explainability there really gets an added value. On the other hand, it also enables us to do more use cases with these detections. For example, assume that we have a rental car and we run this object detection before we rent a car and also after it. And we see that an additional scratch is now detected. We can attribute this scratch to that rental. So more interpretable, more valuable. Then the other use case on the right was more of one regression versus classification. So again, we reframed the problem. Here, the customer wanted data-driven sales. And more specifically, they were looking for what is the chance. So predict, give us a hard number of the chance that a certain deal is going to go through. So we did, and but we saw that it was very hard that when that number didn't align with the intuitions of a salesperson, then it was often dismissed. So again, the same story here. We reframed it as a classification problem. instead of giving that one hard number, that one prediction of there's so many % chance that this sales will go through, what we did was classify the most likely reason that it wouldn't go through. And that gave us two things. Again, interpretability, because a salesperson could now see whether that reason actually held any water. And so even if it didn't align with its intuition, he or she had more to play with. But also it provided an actual action point, because we had the reason, so they could tackle that. If the classification was a lack of follow-up, then they could really invest in that, do more follow-up. If it was a cultural fit, see how can we adjust this. So again, more interpretable, more valuable. And the key message here is understand your use case, understand your data, talk to your users, talk to domain experts, see how we can get that quick win, that low-hanging fruit upfront in a project. Moving on to our second design principle, and now we're finally talking about the modeling, right? And we're getting into the domain of the more classical definition of explainable AI, where it's all about, or more about, the models. So what do we understand as interpretable models? Well, these are the models that are interpretable and simple enough to be understood out of the box. So just the way the model works is understandable by a human. And I'll give some examples. The first one, a simple decision tree. Like in this example, we are trying to classify squares, diamonds, and circles. And so in each root of the tree, we're asking a question. Does it have 4 corners? Does it have 90-degree corners? And based on that, we separate our data. So again, very simple example, oversimplified, sure, but easy to reason about. We as a human know what the model is doing. And so if we were to have an outlier in our data set, perhaps a lack of data cleaning, and a rectangle got in there, we can very easily see that it would be classified as a square. So that was the first example. Then the same goes for linear models. Assume that we are trying to predict the price of gas given to two features. One could be the temperature outside, and another could be an index of political instability in Europe, for example. And then we would fit our gas price to that. Just the coefficients added to those features could show us their relative importance. So again, interpretable by design. And then the final one in this category that I wanted to address was k-nearest neighbors, for example. Another one where an example, so in this case, the white data point is classified based on its proximity to other data points. And we see that its two closest neighbors here are green data points, so it will also be classified as a green data point. Again, we understand the algorithm, we can very easily reason about it as a human. Then a bit of a separate category here would be hybrid AI. But I also placed it here because what is hybrid AI? Well, here we are going to be combining our normal machine learning models with some hard business rules. And I'll give 2 examples. First, imagine we have a self-driving car. So with an autopilot ML agent. And the ML agents looking around, probably based on cameras, seeing roads, seeing traffic lights, and so on, and reacting to that. And that ML agent will also have to find a point or a way to go from point A to point B. But on top of that, we are adding that this autopilot agent should adhere to traffic rules, ideally. Maybe we give him some additional maps data so that if he recognizes the road, but there's none on the map, then maybe not take it. But by adding these additional rules, we are constraining the space that our ML agent can operate in. And so we make it a lot more interpretable because it cannot go outside of these fixed rules, these fixed constraints. Another example, for example, then would be key phrase or keyword extraction from text. One thing we could do there is train an NLP model that would take a body of text, extract keywords, extract key phrases, or we could train another NLP model that instead of directly extracting those keywords or key phrases, it would output regex patterns. And those regex patterns would then be used on the text separately to extract those key phrases and keywords. And so the end goal remains the same, but because it outputs this fixed regex patterns, and if you're able as a human, if you're skilled in reading regex patterns, then you're able to exactly know what the model will extract from the text. So again, hybrid AI also falls under the umbrella of interpretable models here. But then, and I promised in the title as well that we would be talking about Shapley values, and this is really the place for it. Because interpretable models are fine, but sometimes size matters, and the simple models simply just don't cut it. We need to go bigger and models that are inherently black boxes. Sometimes that's just necessary, and then feature attribution is the tool to help you out there. So what is feature attribution? It's really the collection of tools and techniques that aim to give insight in how does a model's output or intermediate result correlate to its inputs. And the best well-known here is would be SHAP. Then SHAP is at this point a collection of tools that originally were based on Shapley values. So, and these might be known to you already, but in broad terms, SHAP values are model agnostic, which means that in theory you can use them on every model without having to do tweaks to the model itself. They are also rooted in game theory, where they started from a couple of axioms and defined this is what we would want out of these theoretical values, and then work their way backwards from that to see what approach would satisfy those axioms. They are ideal for tree-based models as well, which might be counterintuitive given what I just said, namely that in our previous design pattern, tree-based models and decision trees are inherently interpretable, which is true. But of course, at a certain point, you reach a scale of a tree that is no longer easily to interpret by a human as well. Maybe it's an ensemble of trees. So that's why we still would want feature attribution in these cases when the scale of the decision tree models grows too large. The same for model agnostic here. So SHAP is model agnostic indeed. So why would it be ideal for tree-based models? Well, because the computational complexity, it scales with n factorial. So for tree-based models, we can do this efficiently. And this brings me to my fourth point here as well. There are some model-specific and efficient extensions. When we go to certain categories of models, we have to rely on approximations that still have a basis in this game theory foundation of SHAP, but is really aimed at approximating them. So the image then shows an example of what SHAP values, what they could look like and how they are used. So let's assume here that this model takes some characteristics of a person, so age, sex, blood pressure, BMI, and then calculates what the chances of a cardiac failure are. So in Shapley values, or in these models, we also have a base rate. So here you see the base rate of 0.1, and that's really across the entire population. So the average output of all people in this data set would be 0.1. And then if we look on the right, how we go from this base rate to the actual output given the person's characteristics, we see that we start from the base rate, and each of these characteristics adds to that value to eventually end up with the output of 0.4, right? So from the base rate 0.1, BMI of 40, a little high maybe, we go to 0.2. Blood pressure of 180, also a little high, we go to 0.3. Then maybe women are less likely to have these failures, so we drop back down. And then finally, a higher age also increases the risk. And so that's how we end up at 0.4. So that's really how we should interpret SHAP values. But of course, there are some model-specific extensions, and this is one of the examples for differentiable models. So this is an approximation relying on integrated gradients. And often we'll use these for vision models. And so, for example, we have two animals here. The top row is a dewitcher according to the classification. And we see that if we look at this image in the context of the dewitcher class, then the the beak lights up in red, which means that this beak is a really distinctive feature for this class in this image. Same for a meerkat, the eyes here really give it away, apparently. So that is where, at this point, we're going to leave the discussion for feature attribution. I know there are a lot of tools, and we can probably fill the entire talk with them. But feel free to ask questions or reach out for more information specifically on these. But for now, we are going to move on to our next design pattern, which is transparency and transferability. So transparency and transferability by knowing your data and by knowing your model. And in that context, we're first going to talk about model and data lineage. And in the image on the right, I have added an image of Kubeflow pipelines. And if you're not familiar with that, it's really a platform to build and deploy ML workflows really in a component-based manner and chain them together into a pipeline. Now, why have I added this here? Well, because in keeping up with this model and data lineage, MLOps is very, very important. And as the image also shows, these ML experiments can get really complex. You have a lot of steps. You have your data loading, data transformation, then your actual train step. Maybe you try out different hyperparameter spaces, different metrics in the end. You update your data set again, run it again, and so on. So it becomes very hard to keep track of all this. And that's why we need good MLOps practices. Because if we want to know what our model is capable of, we need to know what data, what settings, what metadata did it originate from, and that's that lineage story then, so that we can reason about what it can actually do. If it wasn't trained to interpret certain areas of data, then it probably won't be able to do that in production as well. So that's model and data lineage. Now, knowing which data your model was trained on, knowing which other models your model might have originated from is great. But if you don't know what was in that actual data set, then you can't reason about it either. So here I've put a screenshot of Google's Know Your Data tool, where you can really dissect your data sets, take a look at what are my classes, what's my class imbalance, is there some bias in here towards a certain group, for example. So really knowing your data space is also key into making reasonable assumptions about your model, and so having an explainable, complete solution in the end. So validate your model in this data space. And then finally, and this is the last design principle, intuitive visualizations. Of course, this is just like the first one, pretty easy to understand what I'm going to talk about here. But again, it is vital. It's really instrumental in not only showing the user and explaining the user what you're doing, what the solution is doing, but also leveraging the additional benefits that you have gathered by applying the other design principles. So use the information that you get from those design principles. And again, the two examples I have here on the left, so the problem reframing. So object detection is great, but then show those detections to the user. Make sure you do that so that they can confirm or dismiss these detections. And then on the right, this is an example of GradCam, where we did deepfake detection. So the image of Tom Cruise here is a deepfake. And through feature attribution, we've been able to see where our model, our deepfake detector, focuses on. And here, apparently, the hair and the shirt on the bottom left gave it away to our model that this was a deepfake. So great that we have this info, but again, if we don't show it to the user, if we don't give the user these tools, they're not giving any additional benefits. So intuitive visualizations are very important as well. And so that was the last of our 5 design principles, but I would like to still conclude this discussion with 2 common pitfalls here. And the first one is correlation is not causation. That's true in life and that's true in ML. So we have to be very wary about representing these results correctly to the user as well. Because most tooling, and Shapley is one of them, focuses on correlation, not causation. So if you don't look at your data, don't try to reason about it, then and you have some data that gives you, for example, ice cream sales and also the amount of people that get a sunburn in a given day, you use ML, you use Shap to explain it, then you might as well find yourself in a customer meeting where you are explaining that ice cream causes sunburn, which of course is not true. There is a latent variable that would in this case probably be, it was a sunny day, so people buy ice cream. It was a sunny day, so people get sunburned. But be wary about that. It's easy to see in this example, but sometimes it can be very tricky on real life data to actually see these patterns. And then the second one, out of domain data. So this ties back to the transparency and transferability one. If you don't know your data space, you might as well have ML models that take a data point that is really an outlier towards your training data set, and have your model very confidently but wrongly classify it, for example. And we can see this as the case with k nearest neighbors. So again here, the same example, we have a white dot that we need to classify, and we see that it's not really close to the green data points. It could be that it's a green data point, but it's probably more likely that it's a separate class. So out of domain class that was not in your training data set, that will now be very confidently classified as green because all of its closest neighbors are green data points. So again, something to look out for. But with that being said, we have made our way through our 5 design principles. And at this point, we're going to take a look at one of the use cases that we did. And this one we did for Balta. So Balta, if you don't know, it's one of the leading manufacturers in textile floor coverings. And the project that we did for them was about rug folding. So maybe first localizing this project in where exactly does it fall from ML model versus human capabilities. And it was a bit mixed here. It started out with an ML model where we were weaker than a human counterpart, right? So there we were looking at how can we improve the model, seeing that we got this information. And then it slowly progressed towards AI is on par, where then the trust building became more important. So with that in mind, we'll jump into this use case and see how we can apply the design principles that we just talked about, or how part of them were relevant here. Now, the actual use case that we're trying to solve is, so the high-level objective, a rug is sliding over a conveyor belt. We have cameras on either side, and we need to accurately detect the location where we need to fold the rug. And so we then need to steer the machine in real time to do this. And you can see on the animation, the correct line here is in blue. But there's a large variety of rugs, many different fabrics, patterns, colors. So this is a real challenge to create a model that really accurately can detect this in all cases. The goal of this process here is to then pass a manual quality assurance and quality inspection. So with that being said, and also knowing that our model was weaker than humans at the beginning, how do we create a solution where we allow an imperfect model to control a critical point in the manufacturing process, and we need to give it control of that process so that it can improve over time? Well, there were 3 key aspects into doing that. And of course, relating back to the design patterns that we just saw, they're out of order, but my story makes way more sense if we will talk about them in this order. So starting with the visualization of model outputs. And there we need to realize that a manufacturing line is a really complex environment. There are a lot of different actors, a lot of different processes that contribute to the end result. So a mechanical component could fail, or model could fail, or it could be a human error. And so it's very important to really know what the contribution of our model was, and a good visualization goes a long way, right? So there is a real-time visualization of these outputs next to the line so that we can see, is our model performing well? Does it struggle on this type of rug, for example? Or is there another source for the errors that we are seeing at this point? Now, with this information then, because knowing where our model struggles on which type of rugs, that allows us to do that active learning again. So because on the line, we are continuously collecting data. The data is then uploaded to the cloud, where it can be labeled according to the priority of how bad was our model on this data. Model is retrained, and if it is accepted according to its metrics, then it is pushed back down to the manufacturing line. But very important here is transparency and transferability. Because we have identified the carpets where a model struggled on, we have identified them as a high priority to retrain on. And so because we have this entire loop from data collection to model retraining to, again, deploying it on the line, if we keep track of what we've trained on, we know what we can expect our model to be able to handle at any point. We know what types of rugs we have trained on. And so that transparency and that transferability was also key in this project. And then finally, an interpretable fallback model. So of course, we've talked about the retraining loop in the previous step, but that takes time, right? We are collecting data. That data needs to be labeled or reviewed by hand, which takes time. And then we have the actual training step. And depending on model size and data set size, that also takes an amount of time. And so we cannot simply halt production for a couple of hours until our model has retrained and then hope that the additional data was enough to tackle the troubles it was having. And so that's why we built an interpretable fallback model. If we see that it is going wrong, there is a simpler model that we can activate just for one type of rug. And because it's interpretable, we can tweak it by hand. It's based on more traditional computer vision. So very understandable, tweakable by hand, just to be able to process that one type of rug. And of course, it's not as performant as our big model would be, but it's interpretable, and it gives us the option to, when the model is struggling, have that as a fallback. And so that builds a lot of trust. Because even an imperfect model then, even with our training pipeline, we know that we will always be able to process what is currently on the line. And so that really allowed us to build that initial trust, to make sure that we had a solution that worked in this context, that could improve over time, and that make sure that they didn't have to halt production at any point. Right? And so that concludes this use case. And also then concludes our discussion on design principles so far. So maybe summarizing what we have mainly talked about today. And I think the most important thing to understand here that explainability, at least for us, is a project challenge. It's not a model challenge. From the data, through the model, ending up in the user interface, right? And so then using these design principles from the problem definition, where we can do problem reframing, towards model building, where you can choose for a model that is interpretable out of the box, or use additional feature attribution on top of a black box model. And then finally get to that deployment and that visualization of these results. And all through that process, we want to have good MLOps practices so that transparency and transferability are also part of it. So that concludes my presentation for today. I hope you enjoyed it. I hope you learned something, and I'm very curious if there's any questions or feedback.
All right, Arne, thank you for your presentation. I saw that there was already one question in the chat from Silvio, speaking about tools. In ML6, do you use GCP Explainable AI? Or are there any other open source alternatives that we could recommend?
Yeah, that's a very good question. Well, of course, every approach we have to explainable AI differs largely from project to project. It's always on a project basis that we look. And so there's no default go-to. That being said, we do use GCP a lot, and especially with recent changes, for example, to Vertex AI, a lot of tooling has been part of that process. So indeed, Vertex pipelines, for example, that already captures a lot of ML metadata, and so really helps for transferability and transparency. If there's a good solution on GCP, so Google Cloud Platform, then for the people who don't know, this will be where we look first, yeah. But again, we have to see on a project by project basis.
And maybe to add to that, Silvio, on our website, there's a webinar available on demand where GCP also gives a demo of Vertex Explainable AI. So that could be interesting for you to look at. Then we have another question from Bastiaan about SHAP values. Can you see the question, Arne, or should I elaborate on it? He's asking whether there's a certain rule that we apply for a threshold for the number of features allowed when we're using SHAP, and whether this is a decision based on computation time only.
Yeah, that's a very good question, and I'm afraid I again have to reiterate some of my answer to the previous question. Very project dependable. Of course, sometimes you do have to cut through the noise and indeed look at which do some feature engineering, which makes sense. Can we keep this much complexity, whether it be for computational efficiency or just the human interpretability about it? If you have SHAP values for over 2,000 features, then you cannot reason about them anymore. So quite often, yes, we would, at least for the interpretability part, restrict ourselves to a subset of features where we maybe have some suspicion of what is going on. But yes, we have to cut through the noise at some point. But again, no hard rules to thresholds or something. It's on a project per project basis.
Then there's a more general question from Tom, who's asking whether explainability is more important for end users or for the company developing the models, or both.
Mm-hmm. Yes, indeed. I like that question. There's I think it's definitely both. So when we are developing our model, explainability helps us debug our model in a kind of way. If we find error modes, then of course we will also try to address them in the way we train a model, maybe tweak our loss function here and there. So it's definitely important for us. But of course, we do projects for our customers. And in the end, it's them who need to get value out of the model. So when managing stakeholders for a project, presenting them those explainability numbers, presenting them with insights. So especially in the case we saw, for example, where AI is stronger than humans, where AI has to explain something to us, explain insights into the business flows of the customer, then explainability definitely helps for the customer as well. So I think it's a win-win on both sides, indeed.
All right, and then a last one from Sarah. How can we measure or indicate if explainable AI works?
Okay. Let me try and see if I correctly understood the question, because it's pretty broad. But I think that also ties a bit back into the correlation causation. You can always make interpretations of your explainability metrics that end up to be wrong. So you definitely need to have some caution in doing that. So in a lot of the cases, you have to maybe talk to your end users, like, does this make sense? Can we validate that maybe through your infrastructure, if what we're seeing in this explainability metrics is right? And if we can, you always have to be careful with the results indeed. So again, there's no one solution fits all approach here. But talking to your end users and really validating your results would be the first step, I guess. Yes.
Yeah, I think that's a good one. I think explainable AI is about building trust, right? So if you feel that your end users are trusting your solution, then you probably did the right thing throughout the entire project. There's one last one. I'm not sure whether we have an answer to that. Whether there's any book or course that we can recommend on explainable AI.
Yes. I think not indeed any course or book comes to mind, but Julie, I think we have some internal resources on that we can or that available to the public as well.
Yeah, indeed. So there's no real book, but we have a number of great blog posts about the topic. And we will share those references also on our website in one of our blogs coming up. So feel free to follow us or check us there. or subscribe to our newsletter to stay up to date, and we'll publish some of those resources there.
Yeah, and maybe one additional remark there from my side. I know that Google also has a great research. It's called People plus AI Research, so PAIR, which also have a great number of resources, including some on explainability. So definitely do check those out as well if you're interested.
The the questions keep on coming, Arne.
Great.
Are you still up? Are you still up for a number more?
Yes, absolutely.
More? Okay. Um, so yeah, Tom was saying you said that the design patterns we exposed were ML6 exclusive, and asking whether we based that on another company or paper.
Well, ML6 exclusive, and this is the way we do it at ML6, and we see that this differs from the traditional, more narrow view that is really model focused. So to those interpretable models, to those feature attribution tools. I'm sure there will be some other companies that have a similar mindset to us, but I don't think that we are basing it on a paper or another company. It's something that has naturally grown throughout our experience on projects, and so that's our preferred way of tackling it at this point.
Yep. Then we have one from Michael. You mentioned the difference between correlation and causation in explanations made by machines. Would say that, broadly speaking, all explanations should rely on causation or perceived causation? Not sure I completely understand that question.
Yeah, good question. I think a lot of ML research at this point is basically looking for correlations in your data so that it's really hard to fix causation in there. Of course, causal ML is its own separate subdomain. So there are definitely efforts to do that. Now, to say I think that finding correlations is not useful at all would be a simplification and not true. Or at least in my opinion. It's just something to be very careful about, because if you represent something as causal while it is a correlation, then you might end up with some very wrong action points that you take out of that. So there's definitely value in doing research into more causal ML and finding those causalities in the data. But there's also definitely value in finding those correlations and then reasoning about where they might come from.
All right, and then the last one for now is from Karin. What is the arguments or benefits that we should use to convince companies to invest in explainability?
Okay, yes, another great question. I think when you are making your business case, that ML is a great step forward, or ML in itself is something to invest in. Then explainability kind of comes included with that, because if you want to explain why ML works somewhere, you have to be able to also address the failures, because otherwise it's a bit about from machine learning times, and by giving the argument that let's invest in explainability early so that we know what it can do, what it can't do, and how we can tackle it. But indeed, asking for time, asking for additional effort to put or to get that explainability might not always be easy in every context. But I think it's worth investing upfront, or at least talking about it upfront with your customers.
All right, great. I think that's the last question for now. Thank you again so much, Arne, for this. And thank you all for your attendance today. We hope you enjoyed it. And to discover the other events happening in the European AI Week, you can go to the AI for Belgium website, where you can find the entire overview. So thank you, and have a good day.